Special relativity is pretty crazy. I'm sure you know that when you look into outer space, you're basically just looking back in time. Well, the same goes for the aliens then, right? So the aliens, they see Earth's past, right? And so basically if you were this alien here, you'd be seeing something like, oh, I don't know, Napoleon or something, right? But as you go further back, maybe this guy, he's seeing the dinosaurs. And over here, Earth maybe hasn't even formed yet or something. So what would be really cool is if we could somehow teleport out here and then instantaneously turn around and then we'd be able to see our past. That'd be pretty weird. Now it's important to understand that if we have a train that's moving in this direction, then it would have a Vtrain right here. With respect to this particular observer, he would see it as a positive velocity moving away from him. But that would essentially be the same thing as if this train, as he's moving, he kind of looks out the window and he notices that this observer is just moving away from him at a negative velocity. So this would be just going in this direction with a negative V observer. So either one of these perspectives is correct. We can either say that the V train moves away from the observer at a positive velocity, or we could say that the V observer moves away from the train at a negative velocity. Now let's look at another perspective. Let's say we have a guy in a train over here. The train's moving in this direction here, and the guy's just inside. Now he is going to be sending a light beam from the bottom here, this mirror, to the top mirror here. It's going to reflect off that mirror and just come straight back to the bottom. Now he's in the train, so he's just going to see the thing just go up and then come back down, and that's just basically going to be it. So he's going to measure this distance as being like, I don't know, d going up and then d going down, so 2d, right? 2d. That's what he measures. However, we have this eyeball out here that's basically seeing this train move by. So the train is really moving through here over time. And if he were to start measuring at the bottom there, he would notice that the beam actually moves in space over here, hits that one, and then comes down over here and hits that one. And so when he tries to measure this, he's going to be like, no, that's not 2D. That's like, I don't know, 4 or 5D or something, right? So that's a much bigger distance than what that guy measures. So both of these two people are measuring different distances depending on how they're looking at it. So if he's moving with the moving object, then he's going to measure a shorter distance. And if he sees the object move, then he'll measure a longer distance. Let's define some coordinate systems. We're going to define SO for the observer. He's just going to be in the regular old X and Y that we're familiar with, the horizontal and vertical axes. And this is going to be sort of like X, Y, and Z, and then we're even going to have the CT dimension here, so that way we can multiply velocity times the time and we'll get a distance out of that. So that way we can have a 4-dimensional distance system. This is going to be for a still observer, and we could see the eyeball right there. Now we'll define the S prime, which is going to be the perspective of the pilot here. So from his perspective, his own system is just completely still, right? But from the eyeball's perspective, his system is actually moving over here. So we're going to prime that. We're going to say X prime, Y prime, and then Z prime. Then we're going to say CT prime. And so this is going to be the pilot's perspective. He's the moving system. Now, if we were going to try to take a differential of these systems, we would do something like ds squared is going to be equal to dx squared plus dy squared plus dz squared plus dc squared t squared. And this would essentially describe the world line, which is going to be the path that a particle takes through space-time. Let's consider this guy right here. He's just an observer, but the velocity of the observer with respect to the observer is going to be equal to 0. So we're going to say that he is in fact moving through time, but only through time. And he's going to be stationary through space. So we'll have some sort of an observer time and observer space. Let's send him down his timeline here. We'll call that TO, and we'll label that still time because he's not moving. But over here, we're going to put the space line down. It's just going to be kind of this dotted line because it should be there, but he's just not moving down that line. and we'll label that the observer spaceline. Now let's say we have a train, and the train's going to be moving this direction, and he's going to use some sort of velocity, the velocity of the train with respect to the observer, and we'll prime him. Now he's going to be moving through time and space, so let's move this timeline over here a little bit. But at the same time, I'm going to need to get a little angle here. So this angle alpha is going to need to be on the other side over here. We're going to twist his spaceline a little bit, just like that. So that way, we could keep things consistent from his point of view. So we got two alphas right here. So we kind of had to fold in the axis a little bit to keep things in perspective. But let's go ahead and label this one x of the train. So that's going to be the prime version. And this is going to be the time of the train, which is also going to be the prime version. Now let's consider a passenger who's running on the train in the same direction as that train, right? But let's say the train decides to flash his headlights. So here's flashing his headlights. And then maybe sometime later, this guy in the passenger, he has a flashlight and he flashes that as well. So this guy over here, he's going to see two flashes of light, but he doesn't really know which one comes from which. And so we're going to have to sort of figure that out later. But essentially here we would get this velocity. Velocity here we would say the velocity of the flash with respect to the observer. And we'll call that a double prime velocity here. So he's moving much faster through the space-time. We'll give him a sharper angle here. And then we're going to have to twist this axis as well in this direction. And so we could label this one as the space for the flash, and then we'll call that double prime. And here we can call that time for the flash. We'll say double primed as well. So what's happening is these lines are trying to converge here towards the middle. So if we draw a line over here, and then we also dot that line here, because both of them are going to be sort of twisted to the same point, here we're going to get that 45-degree angle. So this is going to be representing time for the speed of light over here, but also it's going to represent space for light as well. And so they actually happen to be the same line. And that ends up being an issue, but we can now derive what this alpha is. If we wanted to take the tangent of alpha, then we could just basically compare, okay, if this is the speed of time, it's actually going to be the same speed of light, and then we'll compare this speed of this train right here, and we'll compare that over the adjacent side. So opposite is the velocity of the train, adjacent is the velocity of this time here, and so we can kind of basically get the velocity of the train with respect to the observer on top divided by c, which is the speed of light on the bottom, and so that's going to give us that angle. And we could double check that by saying, okay, well, if this was the speed of light over here all the way, and then we divide that by the speed of time, well, actually you could just get 1, and the tangent of alpha equals 1 implies that we have a 45-degree angle. Let's go ahead and follow the timeline down our observer's line. And we're going to end up, I don't know, somewhere over here. And we're going to call this 10 seconds down the observer's timeline. And what we're going to do is we're going to trace his spaceline across, because his spaceline just goes straight across, so we're just going to go straight across, and we're going to see what happens at the same time. So the observer is going to say this is 10 seconds right here, but once we intersect with this timeline, he's actually got to trace his spaceline back over there, so he's going to trace this angle here, and he's going to note, wait a minute, no, it's only been like 9 seconds for me, so he's going to mark this as 9 seconds right there, and because when he traces his baseline back there, he only sees 9 seconds. Now once we reach this intersection over here, he's got to trace his baseline, which is even more curved, and so it's going to go even further back in time, but he's going to say, since this is going to be more like 6 seconds, so like every time we go further and further, that time is going to get warped more and more and more. Now this angle is going to get more and more steep until once we reach this intersection right here, when light traces his spaceline back down to the observer's timeline, he sees that it's actually 0. And so he notes 0 time has passed. Now we can see that not only do we get a longer time observed, there's a longer time observed here. And then there's kind of shorter times for all these other ones. Not only that, but we actually reach 0 once we reach the speed of light. So that's quite interesting. Now theoretically, we don't have to stop here. We could actually keep twisting that timeline and keep twisting the spaceline back over here. And so then we could follow our timeline somewhere over here, but then we'd have to trace the spaceline over here, and we'd end up looking at negative time. So, I mean, graphically it's possible, but I don't know whether that is possible. Let's just make a note that as the velocity of the train with respect to the observer is increasing, then we're going to get this other thing called gamma, and we're going to see that's also increasing. This gamma is going to be this 1 over the square root of 1 minus v of the train compared to the observer squared divided by the speed of light squared. And so this is called the Lorentz Factor, and basically it's kind of like a v almost, but as velocity increases, the Lorentz Factor increases as well. Basically what this equation is saying is that if velocity equals 0, then we get 1 on the bottom, and then we get 1 for everything, so the gamma is 1 if the velocity is 0. If the velocity is like really slow, then it's like really close to 1, so it's not going to have any impact on anything in our equations later. The problem is if you actually do reach the speed of light, and you get c squared over c squared is 1, 1 minus 1 is 0, and you're going to take 1 divided by 0. And so since you can't do that, you can only really just go up to the speed of light, and so that's kind of the issue here. Well, let's analyze Galilean relativity, and this is for when the gamma is going to be basically less than 1.01, so around 1 here. This is for slow speeds, and this is for maybe the velocity is less than 0.14 times c, which is the speed of light there. This is when you're going to get no time dilation, and so these two things, the time of the observer is actually equal to the proper time, so no time dilation there. And we are going to be considering the blinking headlights situation, so we would have sort of a blink 1, and then this is the blinking headlights. There might be some time passing between there, but then you'll see headlight number 2, or a flash of light number 2. It depends on which one we're looking at here. So let's say we're the observer. And the observer, he's going to see some sort of a moving light in flash 1 and flash 2. It's going to be moving, right? But this is a coordinate, so coordinate 1 might be 0, 0, and then coordinate 2 will be some other coordinate. But this is the coordinate of that light of the observer, and that's going to be equal to the pilot here. He's going to notice headlights flashing. But the thing is, the headlights flashed right in front of him. So this light didn't move. We could say that the change for the pilot's perspective, this is the pilot's perspective over here, perspective. And then his headlight, flash, like it just happened right in front of him. It didn't actually move or anything. So from his point of view, this particular quantity is actually 0. And then we're going to say plus v here of the train with respect to the observer. That's this one right here, and then we're going to multiply that by the t, keeping in mind that there is no time dilation, so this t is going to be the same for everybody. I mean, this is obviously could just go away, and so we could basically see that the light is just simply going to be the velocity of this train. He's flashing his headlight, and then flashing his headlights over there. This makes sense. The position that he sees is simply v times the time. But what if it was the flashlight moving instead? So here we would again have this sort of the flash of light happening at a specific coordinate here for the observer. But that would be equal to now the pilot again would see something, but he would see the light moving as well. So he's noticing this. This is the flashlight, all right, and that's moving for him. But you're also just going to add the vt of the observer here, prime that, and then here's your t. So this is kind of like the same thing. So this equation says, okay, the pilot's going to see a small change. So the pilot is here. He's going to see a small change, right? That little positional change that you see. And then the observer, he's going to see the train's position move. And so the total of those two, that plus that, is actually going to be what the observer sees moving through the space as well. So this works out pretty well for the Galilean relativity, no problem. But now let's take a derivative here. So we're going to take the derivative, the time derivative of that moving light for the observer here. If we were to do that, we see that the position of the light with respect to the observer is going to change, divided by the time, and we'll get the velocity of the light with respect to the observer. And we'll set that equal to, this is the position of the flash with respect to the pilot. So if that's moving divided by the time, then we get the velocity of the flash with respect to his own train, because he's riding his train. And then we could say plus the velocity of the train with respect to the observer, the velocity of the train with respect to the observer, divide the time out. So now you get the original relative velocity equation. So these inner t's will cancel out, and this is just the equation we always use. At this point, you could take a second derivative, so you take d over dt, square these, and then this is going to be the second derivative of the position of the light with respect to the observer. This would just give us accelerations, and it would be the same type of equation. So the acceleration of the light with respect to the observer here is going to be equal to the acceleration of the light with respect to the train, and then plus the acceleration of the train with respect to the observer here. And well, the inner t's would cancel here as well. So we get these nice little equations here that are going to work perfectly fine for classical speeds, but they're not going to work for relativity. And so we just have to realize that special relativity is valid only if the acceleration equals 0. Otherwise, we have to use general relativity. But before we get into special relativity, let's define what a light year is. That's going to be c times 1 year, which is going to be c times 3.1536 e to the 7 seconds, which is also going to be equal to 9.461 e to the 15 meters. Now let's set up the same situation but for special relativity, moving really, really fast. So we're going to have the change of this light with respect to the observer, and that's in position here. We're going to need to multiply that by our little factor over here. So we're going to go 1 minus vt with respect to the observer, square that, divided by the c squared. We're going to set that equal to the change of the flash here with respect to the pilot. We're going to prime that perspective right there because this is the pilot's perspective. Then we're going to go v of the train with respect to the observer, prime that, and then we're going to take the change of the time, the proper time. Again, this is going to be the pilot's perspective. On this side, this is always the pilot's perspective. And on the left side, this is going to be the observed situation. What this is essentially saying is that if we look at this part by itself, we'll see that this is how much the light moved, and this is how far the plane traveled. And this is from the pilot's perspective. It moved a tiny bit from his perspective, but also his plane traveled. So those two distances over there is what the observer will notice the light doing. Of course, you have to multiply it by this factor right here. Time, it's just going to be slightly different. So we're going to go time observed, the same factor here, 1 minus vt with respect to the observer over the c squared. And then this is going to be equal to the proper time over here, the pilot's perspective of how time passes, plus the v of the train with respect to the observer, prime that, and then multiply this by the change of position from the pilot's perspective of that light. Just a little math equation here, and then this is going to be divided by the speed of light squared here. Now the Lorentz transformations are actually a simplified version of these complex equations here, because this is going to assume that the light that was flashing over here that the observer seen was just headlights from the train. And so we would say that the flash of light, the change here, with respect to the pilot at least, that's going to be 0 if this is headlights, right? Because they're just flashing right in front of them. The distance correction is applicable when you want to calculate how far the plane moved. And so what you can do is take the distance that was observed over here, multiply it by the factor 1 minus vt with respect to the observer squared over c squared, and then you could set that equal to the distance that the pilot observed moving, because the pilot's going to actually observe a shorter distance over here, and the observer is going to measure a longer distance. So you have to do a little correction there to see how far the plane moved. That's going to be this component over here. So that component is going to be 0. as well as distance correction, we also have length contraction, and this is when you try to figure out the length of the actual plane, or the train, or whatever. The length that was observed here is going to be equal to the proper length times this factor here, 1 minus v do over c squared there. So we can see that the length observed is actually going to be shorter than what the pilot would see. The pilot's going to see the proper length, because like if this thing wasn't moving and you just kind of looked at your plane inside and you looked inside, you would see the proper length. Even if your plane was moving, if you were inside, you'd still measure your proper length. It's just that the observer would notice your plane is sort of getting shrunk if you're moving. So it depends whether you're that guy who's observing or whether you're that guy who's inside the plane. Now from this equation, we'll actually get time dilation. Again, if the headlight's distance equals 0 here, then this term will actually just go away, and we're going to be left with this over here. So the time dilation formula says that the time observed times that factor 1 minus v t squared over here, c squared, is going to be equal to the change of the proper time observed. And so this is going to be the pilot's perspective again, and this is going to be the observer's perspective. This is obviously proper time, and this is going to be observed time. Let's review this one more time, because the observed distance is going to be the longer one than the pilot's distance measured. It's a shorter distance. The length observed, the length of the plane observed is going to be shorter for the observer, but longer for the pilot, longer length for the pilot. The time observed is going to be longer for the observer, and it's going to be shorter for the pilot. Also, the terms slow clock and fast clock can be used, so we could say that the proper time is the slow clock, and that's going to be the smaller number, and the observed clock, or the observer's clock, is going to be the bigger number, and that's going to be the fast clock. Let's also consider the redshift. So let's say we have a wavelength that's observed. This wavelength is going to look much more red, because this is going to be red shifted, or a longer wavelength. Then over here we have the pilot's headlights. I suppose he'd be flashing green headlights over there. But so this is going to be green, and this is going to be shorter. So you have to multiply that wavelength by this factor 1 plus v, the train, with respect to the observer, divided by c. And you can divide that whole thing by 1 minus the v of the train divided over c. This whole thing is under the square root. Let's note that if we have an observer here, and the observer notices the velocity going in this direction, meaning positive velocity, he's going to see a red shift. But if the velocity is coming this way, meaning it's a negative velocity, then he's going to see a blue shift. And that's a little bit terrifying. Let's return to relativistic velocities, and let's say I wanted to find the velocity of the flashlight with respect to the observer, and that would be this guy right here. We'll make sure that this is only moving in the x-axis, okay? So we'll keep things a little bit simpler. So the x-axis velocity, that's going to be equal to the velocity of the flash with respect to the train, in the x direction here, of course, plus velocity of the train with respect to the observer, and then we're going to divide that, of course this is in the x direction as well, but we're going to divide that by 1 plus v of the f with respect to the train there, times the v of the train with respect to the observer there. Both of these are of course in the x direction, and then we're going to divide that by the c squared here. So that's going to be the relativistic velocities only across the x-axis. Naturally, this yields the VFO only for the x-axis, but if we wanted to calculate the VFO for the other axes, maybe for like z or something like that, then it's still moving along the x-axis, so let's just keep that in mind. But this would be equal to, if there's some sort of component in the z, then we would want to think of it as v of the flash with respect to the train, and this is going in the z direction here, and then we're going to do a square root here of 1 minus v with the flash with respect to the o squared in the x direction, which is literally what we found over here. So we can even make this purple. V of the flash with respect to the o, that's going to be squared, and this is for the x direction right here. And then we could divide this by our c squared. From here, we're going to divide this by the same denominator that we have over here, 1 plus v f of t, and this is in the x direction only. And then here we have the v, the train, with respect to the observer. This again in the x direction. And this is divided by the c squared. Now let's discuss the relativistic energy. So we're usually familiar with the equation that the rest energy is equal to the rest mass times c squared. And so this is the rest energy. Now, if something has momentum, you can actually describe the energy as E squared equals the p rel, this is relativistic momentum, times c squared plus the mass of the rest here times c squared squared. And so this is if you have momentum energy, if you know the momentum. If you know velocity, then you can use E equals, this is the rest mass times c squared divided by the factor that we've been using, 1 minus v squared over c squared. This is for velocity. If you know kinetic energy, you can use E equals the kinetic energy, this is relativistic kinetic energy, plus ER, which is the rest energy. So this is for kinetic energy. And this is if you want to calculate the total relativistic energy. Let's make also a change for relativistic mass. Anything moving really fast, you'll take the rest mass and you'll divide that by this factor here, 1 minus v squared over c squared. Let's also remember that an electron volt is equal to 1.6 e to the negative 19 joules. So let's say we have this electron, and we know the rest mass of the electron is supposed to be 9.11 e to the negative 31 kilograms. Then we also know its rest energy being 0.511 e to the 6th electron volts. And if we look at a proton, then we could say the mass, or the rest mass of the proton, is going to be 1.67 e to the negative 27 kilograms. And so the rest energy of this proton is going to be 936 e to the 6th electron volts. Let's quickly compare the difference between Ke classical, which is 1/2 mv squared, and the Ke relativistic energy, which is going to be this gamma minus 1 times m, the rest mass, and then c squared. This is for the relativistic speed, and this is for the classical speeds. Lastly, for the momentum, we're going to say the p relatives, relativistic momentum of the train with respect to the observer. You're going to go ahead and square root 1 minus v of the train with respect to the observer, square that, divided by the c squared, and then that's going to be equal to the rest mass of this train times the v of the train with respect to the observer. And this is essentially the classical version of the momentum on that side and the relativistic momentum on that side. So there we go. This is going to be special relativity. It's pretty intense.